Hello everyone, IMO 2025 has finished, both dates were set, International Math Olympiad is officially over, and we need to just wait for the results. At the same time, I'll still continue uploading videos for you guys. So today we're discussing problem 3, day 1. It turned out to be quite easy question. Nevertheless, we'll still get it through done. There are still a couple of moments to discuss in this question, a couple of tricks in the book that you need to do. So yeah, I'll walk you through the whole idea of this question, how to think, how to properly write it down, organize your thoughts and stuff like that, and just talk about the importance of a couple of more details. So let's cut out my long intro and what I usually do. We're just going to straight into the problem. I'll still try to make it useful for you guys by explaining the proof and not just talking about it. I'll make it look more understandable, even for the guys that didn't solve this question or don't know how to solve this question. I'll try to make it understandable for you guys. And I also have another board because my mouse broke. So let me know, what do you think about it? Do you think it's better, worse, whatever you think it is? Just let me know. So yeah, okay, let's jump in. Okay, so here's the problem. We have n being the set of positive integers. Function f from n to n is said to be bonza if f of a is dividing b to the power of a minus f of b to the power of f of a. And we need to determine the smallest constant c such that f of n is less than or equal to c of n for all bonza functions. So essentially, you want to bound f of n by n. We want to look about bounding f of n. That's what kind of the problem is. The other thing is that this is a functional equation. So this is a functional equation. Yeah, let's just make it. Okay, and what I'm going to talk about functional equations though is that I'll just yeah, okay. When you talk about functional equations, what we do want to know is about there are a couple of ways to solve them essentially. So the first way to solve a functional equation is plug and chug. We plug some values, we make some statements, we rearrange and look at local parts of the problems, and we try to make conclusions from that. The other thing is interpretation. In some questions, you can interpret the function as a graph, as I don't know, a graphic, like a graph in terms of vertices and edges, and there's interpretation with graph as x and y coordinate plane. Then another thing we can do is iteration. So iteration, it works well when you have two variables or a couple of variables that kind of don't work together and you realize the whole structure is revolving around different orbits and iterations. That's also useful. If you have iterations, it kind of works with the vertices and edges interpretation as well. The other thing is when you have division in the function equation, you want to look at primes. So primes, they always work well with division, and it's always nice to look at f of a. The other thing about plug and chug is when we plug and chug, we want to get simplification in the question. So if we draw, say, from function equation, we can go to iteration, we can go interpretation, iteration, we can go to primes, and we can go to plug and chug. And plug and chug, the end result should be like a simplification. So you want to simplify the expression you had. Then primes, you want to essentially do that as well. So that's kind of like the map of what we want to do. So yeah, that's the map we'll have in our problem here. And we're just going to, like usually when I think about problems, try to structure it well. So try to structure what ideas you have, where do you want to go, think about what paths do you want to use and what paths you don't. So let's think about what paths do you want to use here in this problem, right? So, okay. Let's see. Okay, so first of all, interpretation. There are not many interpretations you want to do here, so that's probably not the right path. The other thing is that iteration. We could have used iteration. It was a to the power of b and not b to the power of a, because here we want to still, at the end, we want to get to simplification. So all the arrows, they eventually want to get somehow into simplification of the problem. in any way, shape, or form. Uh, and by narrowing it, then you make some conclusions. So interpretation is not the way to go, for the reason that there's nothing to interpret here, from what I see. And then from iteration, the problem is we still want to simplify, and in order to simplify this problem, the kind of thing we want to get in when we simplify is exponent kind of thingy. Exponent t, something like x to the power of k minus 1, something like LTE, prime divides something. So these are like the main classic ideas that you can also write down what you're looking for, essentially. So something like this, what we're looking for. Uh, please just, yeah, okay. Something like this. That's like our mind map. And the other thing is that iteration is not the way to go because we can't, after we iterate it, we can't really go to any of these. So there's nothing to iterate because A and f of A will never be equal, B and f of B will never be equal, so this is just bad. Yeah. So these are not to the paths, so the only paths we have is like primes and plug and chug. And we can't go to primes straight away. So primes is a good idea, but at the same time, we can't go to primes straight away because if we go to primes, we want to go into prime divide something. And this is like not very nice because f of a, we don't know anything about f of a. So here we'll mark a question mark, a yellow sign, for the reason that it's like red light, say red light, yellow light, and green light. So it's yellow light. It's a good option if we know something about factors of f of a, but we don't know that yet. So the only traffic that we can go to now, so the only possible plausible way we can go here is plug and chug, and we try to simplify. That's where we want to go. Okay, so let's try to go for plug and chug and simplify. So what can we simplify here? So you don't want to just go into plug and chug when you solve a functional equation. You first want to always aim for simplification. So what can we simplify here? And what we notice is we have f of a and we have minus f of b. So in order to avoid a lot of iterations, we'd probably want a substitution that is a equals b. And what a equals b gives us is f of a divides, and then b to the power of a minus, and f of b. So a equals b, so a to the power of a minus f of a to the power of a. And we see that it simplifies nicely. So f of a divides a to the power of a. The other thing about solving questions is you want to structurize your useful thoughts. So when you have a useful claim, for example, f of a equals a divides f a to the power of a, which is quite nice, you want to do the following. You want to write it down in a separate piece of paper. That's what I usually do. And do like this. Do a little frame. The other thing is also this. Just frame it for a nice diagram. So this will be like the side where we write useful claims. So this is our working side, basically. We're constructors. This is our construction side. On the right-hand side is the final product. So that's the way to think about it. Okay, so let's just move this frame a bit nice. Just move it here. So that's what a equals b gives us. And essentially f of a divides a to the power of a is useful, but it's not that useful because it doesn't really limit what f of a has. And what we know is we want primes. So we want factors of f of a. So the reason we want prime divide something, in order to get prime divide something, we need prime divides, let's just set it back to 20, prime divides f of a. That's the only road we have from here to here. That's the only road we can get. So, and this, even though it tells something about the primes, we can see that it doesn't give us any information about it. But instead, if we do know that if we take now a equals p, we do get that f of p divides p to the power of p. And this gives us that f of p is equal to p to the power of kp, where 0 is less than or equal to kp and is less than or equal to p. And this is much nicer. So now we finally achieve what we wanted to achieve in terms that, let's just move it a bit here, move it a bit up. Okay, now we do achieve this part. We do achieve this traffic from here to here. And now we do change from yellow light to green light because these are all viable options now. So yeah, we can get rid of these question marks. And we know that now it's a bit nicer. We don't have these like stuff that we can't sort out yet. Okay, good. We have all this stuff going on here, so let's use it. So we wanted to go from here to here, p divides f of a. So let's just go for that. We want to plug in uh, for prime. So the only information we operate now is f of p. That's the only good ones. So we might as well try to plug in a equals p and b equals q as well, because that will give us double the information. It narrows the result, but in some cases this is better. So you can plug in for p for a equals p and b equals q separately, then see that nothing happens and plug in both. That's the way usually I do it. So okay, now we have f of a. If we substitute this essentially, and yeah, the reason, if my camera kind of gets in the way, I'm sorry, I had to uh, record the video because in the beginning of the last one I cut off different parts of the video, which was not very nice, but yeah, okay, so from here you can get p to the power of kp, and it should divide. So it should divide b to the power of a, which is q to the power of p, minus q to, like, f of b to the power f of q, so which is essentially this, and then this. And what we also can see is that like this part is kind of bigger, so we can rewrite this like this. Minus q to the power of b, like this. That's nicer. And we wanted to go to p divides f of a, so we kind of want to just simplify that to this. The other thing is, though, we want to simplify that, but there's a little trap, and the trap is that k of p equals 0. So if k of p equals 0, everything is good. So from here, we need to write k of p equals 0, or, and from there, write p divides q to the power of blah, 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 q to the power of kq, p to the power of kp, and then we can subtract p and minus 1, like this. Because q and p are co-prime, we take from p and q, and this gives us the following. All right, and what we also know is that p divides q to the power of p minus 1. So we wanted kind of to get an exponency thingy. So we got that as well. We got this. So everything is looking good now. Now we've got like all the traffic going. So now it's all about technique. And we'll see where we're getting stuck. So like the hardest part is getting from here to here. Once you get here, it's pretty much like just working through with techniques. Yeah. And due to this part, we know that basically, since kq times p to the power of kp is kq mod p minus 1, then we can get that this is true. And from this, we can also multiply by q by p minus 1 and say that this is true. And this is bad because for large enough p, yeah, this is not true. So kq minus 1 should be 1, and it should be 0, so kq should be 1. So what we got now is that from all this stuff we got here, we transfer into our good part of the board, and we get that so kq equals 1 is f of q equals q, and kp equals 0 is f of p equals 1. So we got that f of p equals 1 or f of q equal q. All right, and that's a good claim. So this is obviously will help us in some way. Okay, and yeah, that's what we know. And now when we get this claim, so we got into this claim, the way we can move from this claim, there are a couple of ways. So first of all, what we can do from this step is we can test what happens when f of q equals q and what happens when f of p equals 1. And because we kind of always wanted to get an LT, if we want to get an LT kind of thingy, we wanted the reason why it was a question mark here is because we did have powers, but a and f of a were not equal, right? So we couldn't use LTE or something exponency in here. Now with f of q equals q, that's green light. So these all options are open for us now. So now we completely like open up the traffic. Everything is good. Everything is nice. So right now we can plug in, say, if there is f of q that is equal to q, then let's plug it in and let's see what we get. So a equals q. Let's substitute if there is such q. Let's just, is there a bound? Wait, we can, oh, here we go, like this. Hmm, is this the one? Yeah, this is the one. Okay, if there is such q that f of q equals q, then we know that by substituting a equals q, we get that q divides b to the power of q minus f of b to the power of q. And by Fermat, we know that b to the power of q is b mod q and f of b is f of b mod q. So you get b minus f of b mod q. And therefore, if there are infinitely many q such that f of q equals q, b equals f of b, so c equals 1. Yeah, and so that is the case. So now we know that this case is settled because if q is bigger than b, and then this is just not true. Okay, or f of b doesn't matter. So what we now know is that there are not infinitely many q such that f of q equals q. So this can be paraphrased as for p more than certain constant c, f of p equals 1. That's the same way you can rephrase it. So we know this. So now the only thing we're working with is f of p equals 1. So let's work with that. And by plugging in uh, f of p into a, that will work because 1 divides anything, so we need to plug it into b. And when we plug in b equals p, such that p is greater than c, this will give us what? This will give us f of a divides, and then we go b to the power, well, p essentially to the power of a minus 1. And that's nice because that's kind of an exponential kind of thingy, x to the power of k minus 1 kind of thingy. And this is for all primes p. P in prime, p more than c. And now let's see. Well, f of a and a are constants. We basically fix them and we change p. And we want to see that p varies. So we know that p to the power of a is minus 1. It's kind of like very random because we know that p kind of gives a lot of residues mod f of a. So it's not likely that p of a is 1 always. And the way now we think about it is like, okay, we know that p is what decides the thing. And we know that there are a lot of residues mod f of a of p that sort it out. What now combines residues mod f of a and prime p that we can control? And the answer is Dirichlet. Dirichlet theorem claims that there exists infinitely many primes p such that p equals r mod k mod n if r and n are coprime. And using this theorem, we can say that, okay, we can basically target almost any factor, and we can basically make t anything mod f of a, almost anything. It should be comprimed to f of a. And if we make that, we can see that by making it -1, so by taking r is equals -1, we can achieve this. And this yields that, well, this essentially yields that f of a should be 2 or 1 for all, wait, not like this, for odd a. So if a is odd, then f of a should be basically 2 or 1. That's essentially what is said. Um, so yeah. However, now it's just like casework. So if we know that basically if we take a and b both odd, we know that b to the power of a, it's odd. And if f of b is odd, then we know that if f of b is even, so if we take f of b equals 2, the right-hand side is odd and the left-hand side is even. So that's a contradiction. So basically, so yeah, if f of b equals 2, then this thing should be odd, and then this thing f of a is even. So if there are two f of odd numbers that are both even, then we get a contradiction. But at the same time, we can take a equals b, and we can get f of a divides a to the power of a. So by taking f of a divides a to the power of a, essentially, we get that f of a equals 1 for odd. And now, essentially, if we note that by plugging in a, so yeah, first of all, for our note, f of 2x plus 1 equals 1, which is good. This is nice, but now we see that plugging in a anything odd won't give us anything. And the only way we can move further is by plugging in b is odd. So let's just do that. So let's structure that as well. So let's take b equals odd. B equals 2n. So yeah, say b is odd. B is 2n plus 1. Take 1, whatever. And then we know that for all a, f of a should divide b to the power of a, which is 2x plus 1 to the power of a, minus f of b, which is 1 to the power of something. And 1 to the power of something is always 1. So now we get a similar thing. We get, again, a kind of x to the power of k minus 1 thingy. And again, we have a and f of a being constants. And we learned our lesson, we were doing absolutely kind of the same thing, but now we have the information that 2x plus 1 can be any odd number. So, and therefore, if f of a has any prime factor that is odd, we can take this prime factor, put it in here, and we get a contradiction immediately, or we get that like a equals 1, so, or f of a equals 1. So we get that f of a equals 1, or well, basically, because f of a can't have any odd prime factor, because then this won't be true. Well, yeah, then f of a is 2 to the power of x, not x, y, where y is greater than or equal to 0. Okay, so that's another thing for all a. and even included. And now what we see is that, well, we kind of want to continue plug it in. So since we have f of a 2 to the power of y, we know that 2 to the power of y divides 2x plus 1 to the power of a minus 1. Great. And now we can use LTE because now it's kind of like an LTE kind of thingy. So we want to bound y because y is what f of a. So we know that by LTE, y is less than equal to v2 of what it's dividing, which is this. And this thing is less than equal to by LTE because a was even. So a is even here. Even a. We take even a, and using LT, we know that this thing is less than equal to 2x plus 1 and minus 1, which is this, and 2x plus 1, which is this. And then we know that this thing plus v2a and minus 1. And this thing, we know that we can choose any x, so we can choose x is equal to 1 and get that this is equal to 2 plus v2 of a. And that's actually the best bound because 2x times 2x plus 2 is always divisible by 8. And from here we can say y is less than equal to v2 of 4a. And we know that therefore by taking 2 to the power of y, it's less than equal to 4a. And 2y was exactly f of a, so f of a is less than equal to 4a. So, and here we get that c is less than equal to 4. And yeah, now we know that this is quite a solid bound, so that's probably the answer. So now from here we want to construct something, and the construction goes like this. First of all, we want to sort out this is always true. And second of all, what we want to do is we want to make one of them difference 4. And the way you make that is you want to say for some even, it's 4 times bigger. So if you try f of 2 equals 8, like this, you kind of have to deal with a lot of stuff and it doesn't really work out. But if you take the next, if you take f of 4 equals 16, from here, actually, if you take all of others, so f of 2k for k not equal to 2, and if it's equal to 2 as well, then it actually will work out. So what you'll get is we want to show f of a. So if f of a divides something, if f of a is basically 1, then it's always true. If f of a is equals to 2, then we had a being even, right? And therefore we do know that irrelevant of the b and f of b, so thing inside and thing outside is the same parity. So b to the power of something minus f of b to the power of something will always be divisible by 2. So this is true as well. So that's the way you think about like setting up something for f of 2. For even is basically it's always divisible by 2. So that's a good bet. This is a good bet. This we know for sure. And then what we have left is that we need to check for f of 4, and you'll see why f of 4 works. The reason why only f of 4 works is because if you take f of a, which is 16, you wanted to divide b to the power of a, which is b to the power of 4, and then minus 1. For odd and for even, it's already like 2 to the power of something, which is 16, I think. And this is always divisible by 4, so that's good. And then for odd ones, this is always true as well. The reason is it's just LT, so the thing here is v2 and then b plus 1 plus v2 b minus 1 plus v2 in 4, which is 2, and minus 1, which is 1. And this thing is divisible, v2b minus 1 and v2b plus 1 in product, they give like b squared minus 1, which is always divisible by 8, so this is more than equal to 4, and we're done. So yeah, this is a very organized way to show a proof. I hope my video camera didn't get in the view this time, so that's what I hope for. Another thing I want to say is this is about talking about writing down proofs. I think my working here was pretty neat. So I think you could take away the mind map, the method where you basically draw one side and then the other side. So you do one side on one side, the other side on the other side. So where you write useful stuff and where you're just working. And mind map is also a good way to go about solving questions and realizing what you want to do, what you don't want to do. And yeah, I hope the technical moments were clear as well. And yeah, thank you everyone for joining in. I'll try to upload the problem 4, problem 5, problem 6 in the next few days. Yeah, subscribe, whatever. Thank you everyone. God bless.